This lecture is the first in a 5-part series about EEG montages. In it, I will talk about general concepts regarding montages. This talk has 2 sections. The first section will follow a conversational format. The second will be conducted in a question and answer format. So I will start by providing you with some definitions. 2 electrodes, here represented as FP1 and F7, connected to a differential amplifier, constitute a derivation. An orderly arrangement of derivations constitute a montage. The waveforms produced by the potential difference between 2 electrodes attached to the same differential amplifier over time is a channel. All the channels together constitute a tracing. A tracing is an electrical picture of the brain at a moment in time, and as such is called an electroencephalogram. This frame shows an epoch of an electroencephalogram. An epoch in EEG lingo refers to a segment of time, let's say as it is in this frame 6.6 seconds or more commonly 10 seconds, chosen by the electroencephalographer as the unit of time to partition the entire record for reviewing and description. An electrical event, more appropriately called an electroencephalographic representation of an electrical event, is a structure chosen by an electroencephalographer as a pattern of interest. In this case, the electrical event is a single spike. And in this case, a spike and a slow wave complex. An electrical event can be produced by an infinite number of voltage sources, configuration, or generators within the head. This issue is called the inverse problem. On the other hand, where we do know all the qualities and configuration of a voltage source or generator and the medium between the generator and the capturing electrode, we would be able to correctly predict its EEG electrical event representation. This is called the forward problem. The forward problem, as I just told you, has a unique answer. The forward problem can be resolved using the Poisson's equation. This equation states that if we know all the qualities of a voltage source or generator in the brain, that is its location, gradient, and magnitude, and in addition we also know the geometry and properties of the volume conductor, that is the shape of the head, and the conductive properties of the tissue between the generator and the scalp electrode surface, we would be able to predict the corresponding electrical event. It is not important for the boards that you understand the nitty-gritty of this formula. I have taken the clinical neurophysiology boards 3 times and passed them, thank God, without knowing the nitty-gritty of this formula. But it is important that you understand the general concept and its implication. Being as it may, the forward problem is not what the electroencephalographer faces every day. It is the inverse problem, what we have to wrestle with on a daily basis. Nevertheless, despite having no unique solution for the inverse problem, using certain assumptions, the voltage source or generator can be correctly approximated in a significant number of times. Some of these assumptions are that at the moment of an electrical event, all the scalp electrical activity is the product of one generator with a single polarity facing the electrode, or at the most, one generator with two polarities facing the electrode. Here in this frame, I have represented a negative potential in red and the surrounding area in pink. Here in this new frame, I am depicting two polarities, the positive polarity in blue and the negative polarity in red. A second assumption is that the head is a perfect sphere with uniform homogeneous volume conductor properties. A third assumption is that the dipole or dipoles generating the scalp potential are always perpendicular to the brane surface. And the fourth assumption is that at least one of the recording electrodes is in a position capable of capturing the electrical field produced by the generator. Of these assumptions and others not mentioned, the only one we can do something about is trying to put a recording electrode over or close to the generator. For this purpose, the American Clinical Neurophysiology Society guidelines from 2016 recommended to use 21 electrodes, to use the 10-20 system for electrode placement, to simultaneously display no less than 16 channels, and to use at least 3 different montages during the review of each electroencephalogram. So it derives from what I have just said that an important aspect of EEG interpretation is localization of the voltage source, and that using the right montage is important to achieve this goal. This task, that is the task of selecting the right montage, has been made significantly easier by digital EEG. Digital EEG allows us reformatting. Reformatting allows us to see the same event during the EEG review process using different montages. This was not possible with the all analog machines when papers were being used for recording. Yet, while analog EEG machine gathers data from multiple angles depending on the montage chosen at the time of the recording, for example, in this instance, using the montage represented on the arrow, FP1 is viewed from an F7 perspective. And with this other montage, FP1 is viewed from the O1 perspective. The digital EEG machine, on the other hand, gathers all information from the same point. That is, it uses one common reference electrode. We will call this electrode the digital common reference electrode. This electrode is usually placed just behind ZZ, and it is used to gather all the actual data. Then the digital EEG uses this data that is the value of each electrode, in relation to the digital common reference electrode, to perform mathematical operations and give us the value of FP1 in relation to F7, the value of FP1 in relation to O1, or if we so choose, it will give us the value of FP1 in relation to itself. So in reality, changing a montage during digital EEG reviewing, and now all EEGs are digital, is not viewing new information gathered from different perspectives, as it was in the classical world of analog machine. It is looking at the same information processed in different ways. Yet, the end product of analog and digital recordings, that is the EEG itself, is so remarkably similar that when reviewing a digital generated EEG and surveying each channel, we can forget that what we are looking at is the product of mathematical wizardry and analyze it as if the channel were the product of direct inter-electrode comparison. It is for this reason that for the rest of this talk, I will talk about each channel in the classical sense as being the product of direct comparison between electrodes being analyzed. So the age-old question regarding EEG interpretation, which montage to use to record an EEG, has changed to which montage to use when reviewing an EEG. I'd like to start considering the question about the right montage, and notice that I have not said answering this question, but just considering it, by bringing out three issues. The first one is brain activity and noise. The second is pattern recognition, and the third one is source localization. I will start talking about brain activity and noise. Every epoch of an EEG and every and each individual channel recorded in that epoch is the sum of wanted information, that is cerebral electrical activity, and unwanted information, that is noise. And that the differential amplifiers are dumb. The most important attribute of a differential amplifier, the common rejection mode, do not process information according to their worth, but according to their similarities. Thus, in a situation where brain activity is equal and the noise is not equal under two recording electrodes connected to one differential amplifier, the epoch so recorded will be full of noise and the amount of cerebral electrical information will be very little. Such an epoch is obviously bad for interpretation. On the other hand, if the brain activity is different and the noise is the same under the two recording electrodes connected to a differential amplifier, the EEG epoch will consist primarily of brain activity and little noise. Such an epoch is good for interpretation. So how can we make all EEG epochs free of noise or artifacts? And the answer is simple: finding a place where brain activity is different and noise is the same. The first thing earlier encephalographer considered to achieve this goal was the location of electrodes in relation to a neutral point. So they decided to connect input 1 of the differential amplifier to an electrode placed in the area of interest, let's say FP1, and to connect input 2 of the same differential amplifier to a ground, here depicted as the ground from a wall electrical socket. The result was an epoch full of noise. So connecting an input 2 of an amplifier to the ground was a bad idea for two reasons. One, a noise-filled EEG, and secondly, as you can imagine, danger of electrocution. Next, they consider placing the electrode connected to input 2 of the differential amplifier to a different body part. Again, this was done with the hope of capturing unequal brain electrical activity and equal noise. Probably one of the first body parts tried was one of the legs. I assume that the early electroencephalographer reasons for choosing the leg was that the cerebral activity in the head and in the leg was obviously different, and noise would be, or so they thought, about the same at both places. But it was not to be so. The noise was too much. They concluded that the EEG epoch collected with the second input attached to one leg was unreadable. Next, in the search for the perfect montage, the early investigator went on to connect input 2 of the differential amplifier to the anterior chest wall. But cardiac artifact was very prominent in the EEG epochs collected this way, to the point of often overwhelming the cerebral activity in many epochs, thus making all these epochs so collected unreadable. Then they decided to improve on the use of an anterior chest wall electrode by using a second electrode in the posterior chest wall or posterior neck and connecting the anterior and the posterior electrodes together to input 2 of the differential amplifier. This way, EKG artifact was greatly diminished, and the cerebral activity was better visualized. But the search for a perfect place to put the reference electrode, that is the one that goes on input 2 of the amplifier, did not end there. Shortly after the last experiment, some early investigator decided to place the reference electrodes somewhere in the head region, but as far as possible from the cranial vault, let's say an ear or both ears. These electrodes positions greatly improve the ability to produce an artifact-free epoch. And finally, the obvious was done, that was to place the reference electrode, that is the electrode connected to the input 2 of the differential amplifier, on the scalp. This placement provided the best results most of the time, yielding relatively noise-free reference, or at least almost noise-free reference. And it is in this fashion that all electrical data is transmitted from the brain to the digital EEG at this time. In addition to recording cerebral activity with no or limited noise, that is to separate cerebral activity from noise, another concern regarding choosing the right montage is pattern recognition. Pattern recognition gives clues as to the nature of a problem. I think that interpreting Chinese symbol is the closest you can get to pattern recognition. Chinese symbols are enigmatic to non-Chinese speakers. EEG patterns are enigmatic to non-electroencephalographer, but both can be learned with effort. The only way to learn pattern recognition is practice, and this practice is helped by using a consistent set of derivation to view all EEG patterns. After pattern recognition, the next factor that influences montage selection is source localization. Source localization consists of determining the lobe involved, the gyros involved, and the depth of the involvement. A good place to start deciding which montage to use is to have a good concept regarding the effect of distance between two electrodes on EEG waves. This frame represents the head with 21 electrodes placed using the 1020 system. I will use this diagram to briefly discuss the effect of distance on EEG activity. I like to reiterate that despite the visual nature of the distance in digital recorded EEG, using the actual distance between electrodes as if each pair were actually being directly compared is a reliable method to conceptualize, analyze, and interpret digital EEG recordings. It is obvious that the distance between FP1 and O2 is more than the distance between FP1 and F3. This frame introduces these two channels. The one on top is FP1 to O2. The one on the bottom is FP1 to F3. I put both together to show you some important difference related to distance. You can see that the first spike amplitude is higher in the FP1 to O2 channel than in the channel using the derivation with electrodes closer together. You can also see that the amplitude of the slow wave following the spike undergoes more amplitude changes than the spike. In the FP1 to O2 channel, the slow wave is higher than the spike, whereas in the FP1 to F3 channel, the slow wave is smaller than the spike. The reason is that the tissue between the generator and the recording electrode behaves like a fast frequency filter, thus decreases the amplitude of the fast wave more than the amplitude of the slow wave as the distance increases. A fact that is expressed in this tracing by the slow wave catching up to the fast wave as the distance between the two derivations is increased. I will come back to this issue shortly. I will do so to explain to you why, despite the high frequency filter effect of tissue, the fast wave has a higher amplitude in the longer distance derivation than in the shorter distance derivation. You can also see the presence of a negative sharp wave in FP1 to O2 channel that is absent in the FP1 to F3 channel. These changes are the consequence of the spatial filtering effect of montages as a function of distance. The first factor is the attenuation produced by the tissue itself. The effect of the attenuation factor can be summarized by the equation stated in this frame. The intensity of a signal is inversely proportional to the square of the distance from the source. Please pause the video and take a few seconds to look at this frame. The arrow points to the generator, that is the source of voltage. The numbers followed by the letter X refers to the distance between generator and electrode. The different color subdivided squares represent the effect of a squaring in relation to increased distance. The fractions in line with amplitude represent the numerical drop in size as a consequence of distance. So, a potential measuring 100 microvolts at 1 centimeter from the source will have an amplitude of 4 microvolts 5 centimeters from the source. In this example, the distance from the source to the electrode is 5 and the amplitude has decreased by the square of 5, that is 25. The second factor influenced by distance is the high frequency filter effect of tissue. We have alluded to this a few minutes ago. The tissue preferentially behaves like a fast frequency filter, as I previously stated. Thus, the fast frequency filter effect of tissue when going from FP1 to F3 towards FP1 to O2, that is when the distance between the electrodes increases, the high frequency filter effect will also increase. Thus, the number of fast activity contributing to all waves will decrease. And since fast wave have more fast activity than a slow wave, they will be more affected. Thus, they will be decreasing amplitude and increase in duration. Their geometry will also be modified more so than the geometry of the slow waves, than those we have just listed. The effect of changing electrode position from FP1 to O2 towards FP1 to F3 is the result of the changes in the opposite direction. The last factor influencing the spatial filtering effect of montage is the differential amplifier effect. The differential amplifier effect consists of changes in the geometry of the wave configuration that occur as a function of the differential amplifier inverting the signal coming through input 2. In this example, the amplitude of a wave coming into the differential amplifier will be a certain size when the two electrodes connected to a differential amplifier are close. I am representing the distance between the two electrodes by the aqua two arrow heads. If we were to increase the distance between the electrodes, as I am representing with the magneta two header arrows, the amplitude of the wave coming into the amplifier would be less because the second electrode is more distant than in the prior example. Yet, as the wave goes through the amplifier, because of the nature of the differential amplifier is to subtract the amplitude coming through input 2 from the amplitude coming into the amplifier through input 1, the end result is that the wave going out from the amplifier, that is the amplifier output, will be of a lesser amplitude when the electrodes are closer, as they are depicted by the side of the aqua differential amplifier, than when the electrodes are at a further distance as represented on the side of the magenta differential amplifiers. Please take a few seconds to look at this number. I think it would be better understood if you do so. So when electrodes are closer together, as in this example pointed by the arrow, since the electrodes pickup areas are closer, their value will be rather similar. Let's say one being 100 microvolts coming through input 1 and through input 2 coming in 60 microvolts. The result would be that the output from the amplifier would be 40 microvolts. When electrodes are further apart, as in this example pointed by the arrow, since the electrodes pickup areas are far from each other, their value will be very different. Let's say 100 microvolts through input 1 and 20 through input 2. The amplifier will then see this and produce an output of 80 microvolt. This sort of explains why within a distance of 10 centimeters, the amplitude will increase. And that is dependent on the fact that the surveying amplitude has to be close to the source in order for this to work. The explanation I used to explain why amplitude starts dropping after 10 centimeters is that at such a distance, the electrode away from the source, the one that goes to input 2 of the differential amplifier, is getting activity from other sources that add up to a larger amplitude entering through input 2 than would otherwise if it would be dependent only on the source that is feeding the electrode coming into the amplifier through input 1. In this frame, you can see some actual examples. In this recording, using A1 and A2 electrodes combined as common reference, we can see the slow wave activity from C4 and P4 and fast wave from C4, F4, P4, and O2 electrodes. In the same epoch, using closer space electrodes, in the C4, P4 channel, the slow wave are gone, and only in the F4, C4 channel can we see the fast wave, although much reduced from what they were in the prior montage. This is another example to show you the effect of distance between electrodes attached to a differential amplifier. The highlighted areas demonstrate a low voltage spike followed by a slow wave at F4, F8, C4, and T4 electrodes. The common reference in this case is A1 and A2 combined. Now, using electrodes at a shorter distance, the electrical event cannot be noticed. The last point I'd like to make in the conversational section of this talk is about describing EEG waves. The reason for this is that most articles in the EEG literature talk about wave configuration, amplitude, and duration without telling us exactly how they went about measuring them. In this frame, I have represented the terminology most often used to name the different components of an EEG wave. Take a few seconds, pause the video if you have to, and look at it. On the right upper portion of this frame, I have placed the icon that you would usually find in an EEG machine that will allow you to measure the amplitude and the duration of a wave. One method of measuring amplitude is from the maximal positivity before the maximal negativity to the peak of the negative wave. Another method to gauge amplitude is from the peak of the negative wave to the positive peak of the same wave. A third option, when the other two options are not possible or accurate, is to eyeball the average baseline during a 1 second period preceding the wave in question and use this point to measure up to the maximum negativity of the wave, as you can see in this frame. The duration is measured from the maximum positivity of the pre-negative positivity to the other side, as you can see in this frame, or in cases where the amplitude was measured by eyeballing the baseline, it should be measured from that point to the opposite side at the same level, again as you can see in this frame. It is important to stress that the same methodology should be used throughout the record. This concludes the conversation section of this talk, leading to the question and answer section. The first question is: current lines and isopotential lines are the same thing? A, true; B, false. This is a representation of a pyramidal cerebral cortical cell. The pyramidal cortical cell is the generator of the electrical activity recorded during EEG. The important pyramidal cerebral cortical cell structures for our current discussion are the apical dendrite with its distal and proximal portions, and the body. At the state of rest, a thin layer of extracellular space in the vicinity of the neuron is positive. If the distal portion of the dendrite is subject to a large enough stimulus, that is, excitatory stimulus, or if the proximal portion of the dendrite is subject to a large enough inhibitory stimulus, the extracellular region adjacent to the distal portion of the apical dendrite will turn negative, thus creating a dipole between the negative distal portion and the positive proximal portion of the dendrite. The potential difference produced by the dipole causes current to flow between the positive and the negative regions of the dendrite. Some of this current takes the shortest route between the positive and the negative pole. Others flow through a more distant area of the available space, thus taking a more curvilinear route. The current lines formed by the flow of current are in this frame represented in green. These lines are as real as the magnetic lines we see when we put iron ore close to a magnet. But they have different physical properties and cannot be viewed by adding iron to an electrical source. In this new frame, extending at right angles from the current lines, I have added a set of red and blue lines. They are called isopotential lines. They are called isopotential lines because these lines, throughout their length, go through areas of current that have the same voltage. In this frame, I have removed the current lines so we can better appreciate the isopotential lines. The isopotential lines can be shown by using a voltmeter. If we take a voltmeter sensor and place it at precisely the same place on both sides of the dendrite, we will find that the voltmeter will indicate a voltage of 0. If we move both sensors the same distance in the same direction, we would again get a voltage of 0. That is so because in both instances we have placed both sensors at the same isopotential line. On the other hand, if we move the sensor and place them at different levels, as I have done in this frame, we will get a non-zero value. In this case, I have capriciously used 200 microvolts. If we were to move one of the electrodes to the other side but place it at the same isopotential line as it was before, the voltmeter will show the same as it did last time. In this frame, I have added values in microvolts to some of the isopotential lines to illustrate the relation with each other. As you can see, this isopotential line is minus 100 microvolts here, and also minus 100 microvolts in the isopotential line pointed by the arrow. This other one is negative 600 microvolts. It is important to keep in mind that an isopotential line is a boundary and that it implies that all the areas inside of it will have a voltage of negative 600 microvolt or higher in this case. So the answer to this question is false. Next question. In the head, the isopotential lines generated by the apical dendrite of the pyramidal cells are curved to adapt to the anatomical configuration of the head. A true, B false. In this frame, I have represented a dipole with the electrical current as green lines with an arrowhead. The arrows head indicate that the current travels from the side of maximal positivity to the side of maximal negativity. The relation between maximal negativity and maximal positivity can be expressed numerically as indicated by the arrow, with 0 being the point at which polarity shifts from positive to negative in the dipole. I have represented 0 by the blue and red dashed line in this drawing. On the other side, the blue lines represent positivity and the red lines negativity. Also notice the white rectangle. I have placed it there to indicate that the electrical current adapts to the structure through which electricity is being conducted. The whole figure represents a fictitious unidimensional conductor with green current lines and vertical isopotential lines. If we measure the voltage between two segments along the conductor, the voltage will be different. In this case, I have given a value of 100 microvolts. But if instead of having placed the sensors in the direction of the traveling current, we place the sensors at the same distance but at the right angle from the current lines, that is in the same isopotential line as indicated in this frame, the voltage will be 0. Regardless of where along the cable we move the sensors, as long as we keep the same relation, that is in the same line, the value will be 0. It does not matter if it is on the negative side of the dipole or if it is on the positive side of the dipole. The result will be the same. Were we to change the shape of the conductor, as I have done in this frame, by modifying the size of the white lines, the electrical current will adjust to occupy the whole area and the isopotential lines will become curvy to maintain the right angle relation with the current lines. Were we to increase the conductor even further, what will happen will be that the current lines will adapt and the isopotential lines will change with them. And once again, were we to change the size of the conductors once more, the current lines as well as the isopotential lines will adjust to it. Notice that the midline isopotential line, the one red and blue, remains straight. And also consider that we have attempted to represent fictitious one or two-dimensional conductors. But in reality, in the body, we only have three-dimensional conductor. Thus, we talk about conductors in neurology, we always talk about volume conductors because there are 3 dimensions to it. Now I am going to take this figure and turn it. This turn in position will alter the direction of all its components, but not their relation, as you can see in this frame. In this frame, as you can see, I have turned the figure upside down and the negative end goes to the top while the positive end goes to the bottom. In this new frame, I have shrunk the figure in order to make room for extending the isopotential lines as I have done in this new frame. The final addition to this figure is the representation of the pyramidal cell. As you can recall, the pyramidal cells are the generator of brain activity recorded during EEG. So the answer to this question is true. Next question. Isopotential lines can be produced by a single neuron. A true, B false. The figure represents a single dipole from a single apical dendrite of a pyramidal cell. Such fields is therefore often referred to by their orientation of the dipole, and as such they are called vertical dipoles. So the answer to this question is true. Next question. Isopotential map of a single dipole created by a pyramidal cell can be experimentally produced at the boundary of a volume conductor. A true, B false. The isopotential lines of a single dipole, which is equivalent to the electrical field of one neuron, is too small to produce isopotential lines that would reach the scalp. But the isopotential map from single neurons can be detected and drawn experimentally. Here I have represented an isopotential map of a negative field. The map is an expression of the electrical field as represented on a boundary. The isopotential line, often called the voltage lines, indicate the limit between voltage levels. For example, the 30 microvolt line indicates that all voltage inside that line is at least 30 microvolts. The 20 microvolt line indicates that all the voltage inside of it is 20 microvolts or more, and so on at 15 and 10 voltage lines. Isopotential maps can be expressed in 2 dimensions, as I have just done in this frame, or they can be expressed in 3 dimensions, as I have done in this frame. So the answer to this question is true. Next question. All electrical fields are negative. A true, B false. Isopotential map can be drawn to represent negative fields. Isopotential maps can also be drawn to represent positive electrical fields. They can also be represented in 2 dimensions, following the same criteria as we did when we were talking about negative fields, or they can be represented in 3 dimensions, following the same principles. So the answer to this question is false. Next question. The isopotential map of a single neuron can be combined with other neurons' isopotential maps to form an isopotential map of a flat dipole layer detectable at the scalp. A true, B false. Each activated neuron will create a dipole. A dipole will create current lines. Current lines can be represented by isopotential lines, from which an isopotential map can be crafted. This is all true, but only experimentally, because the field created by single neuron is not enough to be detected at the scalp. Isopotential lines from other neurons can nevertheless add up. Here I have represented 2 neurons, and when they get to a certain number, probably in the 10th of 1,000, although in this frame I will represent them just as 3 neurons, a field will appear at the scalp that can be mapped. And the map will expand as more neurons join in. As this process continues, it will produce an ensemble of many neurons. I will represent these neurons in this frame by the figure just introduced, with negative and positive signs that represent a flat dipole layer. As you can imagine, this flat dipole layer containing thousands and probably millions of neurons will create an expanding positive and negative isopotential lines to conform with the volume of distribution. Now I have added a line labeled S to represent the boundary zone, in this case the scalp, and added arbitrary numbers in microvolts to each negative isopotential line crossing the scalp, which will allow us to draw an isopotential map by tracing the isopotential lines at the level of the scalp. The amount of cerebral cortex needed to produce a wave that can be recorded during regular EEG has been said to be 6 square centimeters. So the answer to this question is true. Next question. The isopotential lines from a flat dipole layer can be used to construct a polarity graph. A true, B false. In this figure, I have represented only the negative isopotential lines to make room in the lower area to draw a polarity graph. The first step is to craft a graph with voltage in the y-axis and a space corresponding to the isopotential lines in the x-axis. Then lines are drawn linking the corresponding isopotential lines, that is, joining the negative 20 microvolts isopotential line on one side and the minus 20 microvolts on the other side. In this case, I have used an aqua line to do so. And the same we can do at negative 10 microvolts and also with all the other isopotential lines. We can link them from one side to the other side. The next step is drawing a contour line going through the angular points of the aqua lines, as I have done in this frame. This contour line represents a voltage graph. So the answer to this question is true. All brainwaves generated by a dipole layer can be represented as a flat dipole layer perpendicular to the scalp surface. A true, B false. The representation of the layer of pyramidal cells generating the EEG waves can be made according to the orientation of the dipole created by their activation, as you can see in this frame. The arrangement shown in this frame is the simplest geometrical arrangement of a dipole layer. In this case, the dipole layer is confined to the crown of a gyrus and perpendicular to the scalp. That is, the dipoles are oriented at the right angle with respect to the scalp surface. A group of dipole with this orientation and location is referred to as a superficial vertical dipole layer. Superficial vertical dipole layers show only one polarity towards the scalp surface, thus towards the EEG electrode. In this case, a negative polarity. But this simple arrangement is not the only one found in the cerebral cortex. Other arrangements exist primarily determined by the region of the convolution occupied by the activated pyramidal cells. Most important among these arrangements are when the dipole layer involves the rim of the gyrus, that is an area that includes half the crown on one side of the convolution and a small area in the side wall. This organization can be referred to as superficial oblique dipole arrangement. Another arrangement occurs when the dipole layer is present at the nadir of a gyrus. We will call this arrangement deep vertical dipole layer or arrangement. When the dipole layer is confined to the wall of a gyrus, we will use the term horizontal dipole arrangement. In this situation, the dipole is parallel to the scalp surface. Even more complex dipole arrangement exists, consisting of a dipole layer occupying both walls of the side of a sulcus and the nadir of the gyrus, to which we can refer to as bilateral horizontal dash vertical dipole arrangement. And the last arrangement I will mention occurs when the whole convolution or gyrus is involved, to which we will refer to as a gyral dipole. So the answer to this question is false. Next question. The solid angle theorem of volume conduction provides an intuitive approach to understanding single dipole electrical fields. A true, B false. Previously, I have represented the cerebral cortical pyramidal cell at rest as having a thin layer of extracellular space in the vicinity of the neuron with positive charges. But we can also represent the cerebral cortical pyramidal cell membrane at rest as having tiny batteries with their positive poles towards the extracellular space and the negative pole towards the intercellular region. This representation will allow us to understand the solid angle theorem of volume conduction regarding a single neurons, as you will see. If the distal portion of the apical dendrite is subject to a large enough excitatory stimulus, or if the proximal portion of the apical dendrite is subject to a large enough inhibitory stimulus, the batteries of the distal portion of the apical dendrite will turn so that now their negative pole faces the extracellular space, thus producing a demarcation between the negative extracellular apical dendrite region and the positive extracellular proximal dendrite region. This demarcation line will be labeled 0. This situation creates an extracellular negative region on the top and a positive region below, separated by the demarcation line we just mentioned. If at this point we place an electrode somewhere in the vicinity of the activated pyramidal cell, the volume conduction theorem explains that the area effectively surveyed by the electrode, to which we will refer to as the subtended area or the effective subtended area, corresponds to the area of the dendrite where the poles of the batteries subtended by the solid angle of the electrodes are equal. We refer to this as the effective solid angle I just previously mentioned. And in this frame, I will represent it by a green omega symbol. In this frame, I have highlighted the area inside the effective solid angle by coloring red the negative poles of the batteries inside the solid angle. Notice that elsewhere in the apical dendrite, the electrode will be subtending either negative pole of one battery and the positive pole of the other battery on the top of the effective angle, and the positive pole of a battery closer to the electrode and a negative pole of a battery further from the electrode below the effective solid angle. Thus, the only area viewed by the electrode where both charges are the same is the area subtended by the electrode in what is called the effective solid angle. This area corresponds to a circular structure which represents the cross-section of an idealized dendrite that we have used as a model. In this new frame, I have enlarged the circular dendrite area for better visualization. So the answer to this question is true. Next question. The solid angle is a measure of the apparent size of an object as viewed from a particular point. A true, B false. An object looms larger as it is brought nearer and central to a particular point, even though the dimension of the object do not change. In this frame, as you can see, the dimension of the circular structure at the level of the white line is the same, but their perception by the electrode is different depending on the spatial relation between the electrode and the object. In the figurine on your left, the electrode is higher than the other two electrodes, and it is also off-centered. Hence, the object to that electrode will look smaller than it would look to the other two electrodes. By the same token, when the electrode is closer to the target but off-center, the object will look smaller than when the electrode is at the same distance but is also centered. So the answer to this question is true. Next question. The mathematical approach to finding the effective solid angle subtended by an electrode is to subtract from the total angle the ineffective angle or angles. A true, B false. In this new frame, I have highlighted the area inside the effective solid angle by coloring red the negative poles of the batteries inside of it. The mathematical approach to finding the effective solid angle subtended by an electrode is to subtract from the angle here represented in aqua the sum of the ineffective angles above the effective solid angle represented in magenta and the ineffective solid angle below the effective angle represented in blue. So the answer to this question is true. The term microscopic solid angle is used to refer to the solid angle produced by a flat dipole layer. A true, B false. The term microscopic solid angle is used to refer to the solid angle created by a single neuron. The answer to this question is false. Next question. Changing the distance of an electrode following the same isopotential line changes the amplitude of the recorded potential. A true, B false. This frame represents the changes in the wave amplitude corresponding to the area of the effective solid angle. when the area is viewed by an electrode at the side, the wave will be smaller than when it is viewed by an electrode right on top of it or center to it. But if the position of the electrode is changed following an isopotential line, the size of the wave will be the same despite the different position. This is because, as in this case, what is lost in distance is gained in angle. Or in this other case, what is lost in angle is gained in distance. So the answer to this question is false. Next question. The solid angle theorem of volume conduction provides an intuitive approach to understanding flat dipole layer electrical fields. A true, B false. We already use the solid angle theorem of volume conduction to understand the fields of a single activated cortical neuron. These questions deal with flat dipole layers. As you recall, a flat dipole layer consists of an ensemble of many neurons arranged linearly that, when activated, develop a set of vertical dipole layer. If you recall, I presented this diagram before in this talk when we discussed isopotential lines. And also this one when we're talking about isopotential lines and contour voltage fields. At this time, I will use it. That is, I will use this diagram to show you the relation between solid angle, isopotential lines, and wave amplitude. In this frame, I have represented a wave view from the position of an electrode in a specific area. Now I have exchanged the position of the electrode, keeping the distance but changing the angle. This change results in a higher amplitude wave. In this new representation, I have positioned the electrode in the same isopotential line as it was in the first diagram, where I show you the first wave related to the electrode position. And as you can see, the amplitude is back to what it was initially. So the answer to this question is true. Next question. The amplitude of a wave resulting from simultaneous activation of a 6 square centimeter patch of cerebral cortex at the crown of a gyrus will always produce the same size wave in an EEG. A true, B false. We already use the solid angle theorem of volume conduction to understand the field created by a single activated neuron. We have also used the solid angle theory to explain the behavior of a flat dipole layer. Now I will use the solid angle theorem of volume conduction to explain electrical wave formation in the context of cerebral anatomy. In this frame, I have represented a layer of pyramidal cells by their cartoonish structures in the crown of a gyrus. This figure represents the purely theoretical situation that would result from the activation of a 6 centimeter patch of cerebral cortex at the crown of a gyrus. Once activated, these neurons can also be represented by their negative and positive poles, those producing a superficial vertical dipole, as you can see in this frame. In this frame, I have added an electrode right on top of the crown of the gyrus and the solid angle perceived from that electrode. In this case, there is only one angle, represented by the yellow omega, and this angle is equal to the effective angle, that is the effective solid angle, represented as the green omega sign. Now I will introduce a voltage line chart. I will do this to represent a wave, the wave itself representing the voltage captured by the electrode placed right on top of this crown, referred to a neutral point. Now I am going to change the position of the searching electrode. This new position will yield a smaller negative potential. The answer to this question is false. Next question. Cerebral horizontal dipole arrangement studied with a single exploring electrode right on top of the arrangement and an inactive reference will produce a zero potential. A true, B false. Pyramidal cells in the wall of a gyrus, when activated, produce a horizontal dipole. That is, many horizontal dipoles. Horizontal dipoles look from straight up by an electrode matched with a neutral reference will view a negative solid angle and a positive solid angle. The negative solid angle will be viewed at the point where the dipole is negative, and the positive solid angle will be seen where the dipole is positive. Here they are represented, the negative by the yellow omega and the positive by the aqua omega. The addition of these two angles due to their negative and positive polarities will subtract each other, thus yielding no potential. A more visual exposition can be viewed by introducing a voltage line. The negative solid angle will produce a negative wave. The positive solid angle will produce a positive wave. Since they are both occurring at the same time, they will cancel out, thus producing no potential at that point in time. This is shown in the lower part of the screen by the equation showing the green omega, which is equal to the subtraction of the yellow omega and the aqua omega. So the answer to this question is true. Next question. A cerebral horizontal dipole arrangement studied with a single exploring electrode and an inactive reference can produce a positive or a negative potential. A true, B false. View from a left angle as it is shown here. The activity captured by the electrode, that is by the searching electrode, will produce, in this case, a negative wave. Were we to look at the horizontal dipole from the other end, that is from the right side, the activity produced will be positive. So the answer to this question is true. Next question. Which of the following dipole arrangement can produce an EEG phase reversal? A. Superficial vertical dipole. B. Horizontal dipole. C. Deep vertical dipole. D. All of the above. This frame shows the dipole arrangement listed in the question. A phase reversal can only be produced by a horizontal dipole. This frame isolates the horizontal dipole figurine to show how it works. A horizontal dipole will create a negative field and a positive field in opposite direction. Those fields will be detected at the scalp if they are big enough or strong enough. This situation, that is a negative and a positive simultaneously occurring scalp fields, occurred with generator in the interhemisphere cortex adjacent to the interhemispheric fissure, or on the walls of the convolutions, that is around the sulci or around the fissures. So the answer to this question is horizontal dipole, B. A scalp recorded phase reversal can be due to A. a horizontal dipole, B. an artifact, C. two fields with opposite polarity, D. all of the above. A scalp recorded phase reversible can be due to the presence of a horizontal dipole, artifacts, or two generators with opposite polarities. So the answer to this question is D, all of the above. Next question. The solid angle theory can be used to explain polarity phase reversals as a function of a horizontal dipole. A true, B false. On this frame, I am representing a horizontal dipole that, as expected, is occupying the wall of a gyrus. Above, I have represented a voltage line. On the far left, that is at PI, I have represented the position of the leftmost electrode and the omega symbol to indicate the solid angle it has. In this case, the angle is negative. Translating this information to the voltage line, we have to plot it at some level in the negative portion of the line. I have plotted it just above the neutral line in the voltage line, as you can see. I am going to do the same exercise with P2. Let's just say that the amplitude of P2 is bigger than the amplitude of P1 and that both are negative. This is so because on the balance, the increase in amplitude resulting from a shorter distance is enough to compensate for the loss of amplitude due to a narrower angle. I will therefore place a point to reflect the increase in amplitude at the position corresponding to P2 in the voltage line. It is important to stress that the prior two electrodes, as well as the rest of the electrodes that I will be referring to while answering this question, are being referred to a neutral point. The next position is right on top of the horizontal dipole. As I hope you remember, an electrode right on top of a horizontal dipole will see both negative and positive poles of the dipole with the same intensity, thus canceling each other. this will be reflected at the voltage line by a spot or a dot at the neutral point at the level of P3, as you can see in this frame. At the fourth position, the solid angle will show a positive side or the positive side of the dipole. I have represented this in the voltage line by a blue dot. The blue dot is on the positive side of the voltage line. Finally, at position P5, the solid angle will show a positivity, and despite that the angle is better than from position 4, since the distance is longer, the amplitude will be smaller. Joining the dots together, we will have that a change in direction has occurred. Change in direction in the voltage line is the hallmark of phase reversals. If we then connect the electrodes in a chain as indicated under the arrow, we will see two instrumental phase reversals. On the other hand, if we connect the electrodes to a common reference electrode in a neutral position, as indicated by the arrow, and as we initially capture the recording, those with a negative potential will go up. P3 being neutral will remain the same, that is, will be a straight line, and P4 and P5 will go down, as you can see in this frame. So the answer to this question is true. Next question. An instrumental phase reversal will occur if electrodes are connected in a chain in the presence of a vertical superficial dipole. In this frame, I have represented a superficial vertical dipole. As you remember, superficial vertical dipoles are in the crown of the cerebral gyrus. The superficial vertical dipole, in this case represented with the negative pole towards the scalp, will be plotted on a voltage line as variable negativities, with the maximum at the position or the electrode right on top of it, here labeled P3. Connecting those electrodes in a chain as we did before, indicated over the right side of the screen, we will see an instrumental phase reversal at the level of P3. On the other hand, connecting those electrodes to a common neutral electrode, here represented by R, will yield all waves going up, that is, being negative, with the highest amplitude at P3. So the answer to this question is true. Next question. Activation of a gyrus, that is to include the crown and walls of a convolution, will produce a phase reversal. A true, B false. In this frame, I have represented activation of a whole gyrus, in this case with negativity being towards the scalp. Now I have added the angles view, that is the solid angles view, primarily by all the electrodes placed at position P1, P2, P3, P4, and P5. This viewing will result in the changes in the voltage line shown in this frame. The answer is false. Next question. Why does the magnitude of a potential generated by an activated gyrus produces higher amplitude when captured by an electrode on top of the gyrus than when captured by an electrode on the side of the same gyrus? A. Dipole at the wall are further. B. Dipoles at the wall have a smaller solid angle. C. Both. An electrode only sees the side of the battery or the pole of the dipole facing it, but it does so regardless of distance. An electrode placed right above the crown of a gyrus will view the negative poles of the dipole under it. It will not see any other poles. In this case, this will correspond to 6 negative poles. These poles are being viewed from, let's say, 2 centimeters away. An electrode looking at the same gyrus from the side will see the negative pole of the dipole in the wall close to it, but it will also see the positive poles of the dipoles on the wall further from it. I have depicted this concept in this frame. From this angle, the P5 electrode sees 11 negative poles and 6 positive poles that when subtracted will yield 5 negative poles. So, despite having a wider solid angle, the magnitude of the angle is less. If in addition we take distance into account, we can see why P5 will record less voltage than P3. So the answer to this question is A. Next question. The rate of drop of a potential is inversely proportional to the dielectric constant. A. True. B. False. This formula shows up frequently in neurophysiology books. It states that any potential, negative or positive, created at any point by an electrical charge is directly proportional to the magnitude of the charge and inversely proportional to the dielectric constant of the medium and to the distance from which it is being measured. So the answer to this question is true. Next question. The maximal solid angle subtended by an electrode represents a portion of the maximal solid angle that the providing electrode can potentially subtend. A. True. B. False. In order to answer this question, we must talk about steredians. The steredian is the SI unit of solid angles. The name derives from the Greek stereos to mean solid and the Latin radius to mean ray or beam. The steredian is used to describe two-dimensional angular span in three-dimensional spaces. This is analogous to the way in which we use radians to describe angles in a plane. So in order to understand steredian, I will first explain the much easier to understand concept of radians. The circumference of a circle is mathematically resolved by the formula indicated by the arrow. The R stands for radius. If we take the length of the radius of a circle and stack it at the periphery of the circle as I have depicted in this frame, and without changing its length bend it in order to hug the circumference of the circle, we have rediscovered a way to measure a triangle. We can say that this triangle has an angle of 1 radian, whether we measure it at this point or at this other point. 1 radian is equal to about 57.3 degrees. Half of the circumference is 3.14 radians or 180 degrees. This can also be written as pi radian or 1 pi radian. And the whole circumference can thus be expressed as 2 pi radian or 360 degrees. In this frame, I have added a table comparing degrees with radian measured with pi as a base and with natural numbers. Now that I have explained radians, I will explain steradians. A steradian refers to volume, that is to 3-dimensional space. In the same way that a radian cuts out a length of a circle's circumference equal to the radius, as we have just explained, and a steradian cuts out an area of a sphere equal to square of the radius. The surface area of a sphere is 4 pi radius square. The area of a surface of a sphere equal to the square of the radius is called an steradian. Thus, the surface area of a sphere has 4 pi steradians. Used in natural number, we will say that it has 12.57 steradians. So the maximal solid angle that can be subtended from one point or from an electrode is 4 pi steradians. Knowing this, we can say that the area subtended by an electrode, here represented in yellow, can be expressed as a portion of the surface area of a sphere or as a portion of 4 pi radian. Understanding these considerations allows us to understand the theory behind solid angle theorem. We have already established that the magnitude of a potential seen by an electrode is equal to the magnitude of the charge and inversely proportional to the distance and dielectric constant. So we can substitute charge by the potential as seen by the electrode. We can do this using the magnitude of what the electrode sees as stipulated by its maximal solid angle. So the answer to this question is true. Next question. The terms maximal negativity and minimal positivity are interchangeable. A true, B false. In this frame, I am introducing a voltage line. Notice that the negative value increases as they go up, whereas the positive values increases as they go down. In this frame, I am representing a three-dimensional negative field. The apex is the maximal negativity. The base represents the minimal negativity. Now I am introducing a three-dimensional positive field. As you can see, the maximal positivity is again at the apex, but the apex is now upside down. The minimal positivity is on top. So the answer to this question is false. Next question. Assuming that an electrical event is the product of a single generator, the polarity of such an event can be predicted based on the direction of the deflection in a single channel. A true, B false. It is important to understand that it is not likely that any electrical event captured during EEG recording is the product of a single generator. But it is also important to remember that we have to assume a single generator for us to be able to interpret any event occurring in the brain and view in the EEG. Thus, assuming a single generator in the derivation presented in this frame, the sharp activity can correspond to a positive or a negative generator. That being the case, it will have a single positivity or a single negativity. If the generator of the activity is negative, F4 can be detected to be the absolute maximal negativity of the field in relation to FP2, or F4 may not be the absolute maximal negativity, but still in relation to FP2 it would be the maximal negativity. If the generator of the activity is positive, the polarity of the sharp wave would be positive if FP2 is the absolute maximal positivity of the field when compared to F4, or if FP2, even when it is not the absolute maximal positivity created by the field, is the relative maximal positivity when compared to FP2. So the answer to this question is false. Next question. How should an electrical field confined to a quadrant of the scalp be considered? A. Highly localized. B. Localized. C. Widely spread. D. All of the above. This frame shows the 20/20 system scalp arrangement. One way of labeling an electrical scalp field is relative to the scalp area involved. This is often based on the number of EEG involved electrodes and their relation. A highly localized field usually refers to an electrical field that only involves one or two electrodes. A localized field is usually referred to as the field confined to one quadrant but involving more than two electrodes. A widespread field usually refers to a field extending beyond one quadrant. So the answer to this question is B. Next question. A widespread field with a maximal amplitude of 45 microvolts should be considered A. High amplitude, B. Medium amplitude, C. Low amplitude, D. All of the above. In addition to labeling a field according to its polarity, we can also label a field according to the area it involves. EEG fields can be labeled in relation to their absolute or relative amplitude. Relative amplitude is established using the ongoing record, thus judging the field based on the estimated average amplitude of the record is often used. Another possibility is to use absolute amplitude. Absolute amplitude is judged relatively to the usual amplitude found in alpha activity in adults. Therefore, most electroencephalographers use the later classification, which establishes the amplitude of alpha according to the derivation built from the occipital lobe to the ipsilateral central region. Using this classification, we call a field with a maximal amplitude above 50 microvolts as being high amplitude, a field with an amplitude between 25 and 50 microvolts as being medium, and a field with less than 25 microvolts, that is a field with a maximal amplitude of less than 25 microvolts, as low. The classification of fields according to amplitude is independent of the area involved. It is only based on the maximal amplitude of the field. So the answer to this question is B. Medium amplitude. Next question. All electrical fields have a smooth transition between voltage zones as viewed by the scalp electrodes. A true, B false. As depicted in this frame, most electrical fields have a smooth transition between voltage zones. Thus, if we place electrodes going from anterior to posterior and connect them as a chain, the potential created by such an electrical field will have a smooth transition from one electrode to the other. But this is not the case for all electrical fields. Some electrical fields have very quick transition as depicted in this frame. They are uneven from the point of view of the recording electrodes. Such fields will create a non-smooth appearance of the recorded potentials. As you can see in this frame, the potential created by connecting electrode 1 and electrode 2 produces a large amplitude wave. Such a wave suggests an anterior maximal positivity when in reality, as it is depicted in this frame, it is a much more posterior negativity that is creating the field. So the answer to this question is B, false. This is the end of the first part regarding montage. Thank you very much for your attention.